Second session of Machine Learning Summer School from Amazon, India. In this session, we are going to learn about deep neural networks and why they're used and how they're used. And we will cover three main parts of deep neural networks: MLP, or the multilayer perceptron, convolutional neural networks, and finally, recurrent neural networks. So first, in this first part, we will discuss about deep neural networks and the multilayer perceptron concept and what it is and how it is used. And in the next two sessions, we will go over with CNN and RNN. All right, so let's get started. So in the previous session, you have already learned about machine learning basics, and you already know what is supervised learning and how machine learning models are built, what are loss functions, and why is data splitting done in the form of train, test, and validation data sets. And you have already built a linear model using these details, right? So next, in this session, we will cover some historical context about why is deep learning being used and what has happened earlier in time before the current deep learning revolution. We will then go through the single layer and multi-layer perceptron algorithms, gradient descent, which is used for training these ML models, chain rule, backpropagation, and activation functions, which are all used for the training part. We will see a code example of how you can build and train a deep neural network with PyTorch framework. And then we will discuss some tips and tricks for how you can basically improve your neural networks. So let's get into the historical context. So how did AI solutions start? So first we started with handcrafted solutions basically. So what we used to do is we used to take these solutions which we made by handcrafted algorithms like edge detectors for images. So what you do is you would have an image and you would want to move a convolution filter on top of it. And the way this convolution filter, let's say, worked, and the value of the convolution kernels, all those were defined by hand coded or heuristic logics. For example, this here we have shown an example of edge detection, right? So this will do vertical edges and this will do horizontal edges, and this basically can just do vertical and horizontal edges. If you want to do diagonal edges, then you will have to write a separate detector, or if you have to detect a flower, then you have to write a separate detector, right? So initially we had handcrafted solutions before 2012, and deep learning took off before that. Then we go into learned solutions with priors, basically a solution that we are learning via neural network, but we do have some information that we have hand coded in it. Say, like for example, in this case, this convolutional neural network, if you notice that it's a 3x3 sized matrix that is used for convolution, and the convolution operator basically has sensitivity to locality, right? So uh, every value which is close by is convolved together. If you notice here, every value which is close by is convolved together. So the assumption or the prior, right? The prior that I am assuming here is that nearby information is valuable. So in an image, the close pixels are valuable, right? So whatever is close by is more valuable than what is farther away. Like for example, if you take the example of face recognition, then things like eyes, nose, and mouth are more valuable, while you can say that ears and hair may not be that valuable because they are not very close to the center point of the face. So we took handcrafted priors, but learned the overall network, and that's majorly the progress that has been the deep learning progress as of now. So in the similar lines, RNNs say that the nearest word, the neighboring word, is important, and for that reason, they are also based on the same prior that close things, nearby things are more important than farther away things. Then you have the recent trend, which is the semi-supervised learning, wherein we still have these priors, but we don't need labeled data to learn from. For example, here you can see that I can take a single image of a dog, and I can basically convert the image into two parts, basically by cropping two parts and coloring them separately. And then the neural network, which is a CNN here, its responsibility is to basically make sure that parts which are similar, like the dog, the parts of the dog are similar to each other, should be close together, while parts like a sofa, which are farther away from the dog, should be separated from the dog parts, and the sofa should be similar to the other images of the sofa. So the neural network is basically tasked with finding similar images. And like if I take a one crop of image and the same another crop of the same image, then those should be close together than entirely separate images. So that's the major objective in these kind of networks in semi-supervised learning, basically, that you don't have labels, explicit labels, like the network does not know that this is a dog, but it can do learning on the basis of that this image should be different from this image, and parts of this image should be different from parts of this image. So we another example of the same thing, right? So here what we will do is that we will try to match the same animal, and based on matching the same animal, we can use something like semi-supervised learning, and we don't need the exact label of the animal, but we just need to know that these are two same animals. So here we are still using CNNs and RNNs, and what we are doing is that we are using these handcrafted priors, and we are learning from the data. Next, you have networks which have no handcrafted priors. Like the network is not told that nearby details are important from the very beginning. It's not told that things which are nearby, like nearby pixels or previous word and the next word are important. It's not told those kind of details. It's only told that, hey, here is the data, and use some semi-supervised technique and learn from it. So this is one another direction that we are going, which basically will enable us to learn easily from data. The one of the networks which came out of these ideas is BERT, which basically learns in a unsupervised way, in a semi-supervised way, let's say, and make sure that you don't need to provide labels for each of your data point, but rather the supervision comes from the data itself. So BERT basically predicts each token. If you mask them, then the BERT engine will be able to predict the masked token here. Similar examples in computer vision also, wherein they are using this transformer network to recognize what an image contains. And then where do we want to go really, right? Like what do we want to do with AI? So what do we want to do with this deep neural networks, deep learning in general, right? So we want to build systems which have a lot of capability in a single system, which can learn and let's say play games, answer questions. Like for example, AlphaGo systems have been able to beat world champions in many games, right? Similarly, GPT-3, for example, is a model which is based on text only. It takes input in the form of text only, but it is able to give out answer of even problems like multiplication, subtraction, and a lot of mathematical problems it is able to handle, right? It can even do text generation. So this is a text generated by the GPT model, not by any person. And you can read the text. It's very coherent. It seems like a person wrote it. There is no what do you say? There is no artifact, or there is no easy indication that someone else wrote it, like a AI wrote it. And when they test for accuracy, they notice that only 12% people are able to distinguish between GPT-3 written text and normal text written by a human. Another example of question answering with this GPT-3 model, wherein the model is able to answer questions very nicely. Like factual questions like how many legs does a frog have? 4 legs. And are there any animals with 3 legs? No. So, and some trivia questions also, like why don't animals have 3 legs? Animals don't have 3 legs because they would fall over. So yeah, I mean, it is even able to reason beyond just answering factual questions, right? So the overall goal of AI in usual is to be able to learn from data without human intervention, without labels, without humans having to spend hours and days annotating data. And with only learning from data, we want to get to good systems like GPT-3 and even better, which are able to reason, answer factual questions, do mathematical expressions, and a lot more, right? So the first building block to that is basically our MLP, or the multi-layer perceptron, and that starts the deep learning part, and then from there further and further improvements are being done to reach better networks like transformers, convolutional neural networks, RNNs, and other ways of modeling the data, right? So we will look at some of these things today, and we will also look at why do we use deep learning, what happened that deep learning took off, right? So there are few reasons why we have adopted deep learning compared to, let's say, linear regression, or let's say XGBoost, or any other algorithm which like gradient boosting and other algorithms. Why do we have deep learning, and why is it doing so well? So one of the things that is important is huge amounts of data, right? So you want a lot of data to train your deep learning models with, and with internet penetration and big data, a lot of data became available crowdsourced from Wikipedia and other sources. So huge data is one of the big players, one of the big reasons why deep learning took off. And another big reason, the presence of hardware accelerators, GPUs basically, right? So if you are gaming, if you are a gamer, then you would understand that you need a good GPU to basically run games on high resolution. And that high resolution work is done by GPU by doing a lot of computations. Now, what deep learning does is it leverages the same computation and tries to, instead of rendering a game or a frame of image, it tries to basically do matrix multiplications. And those multiplications basically enable us to do make deep learning models, train these models very fast, right? So what happens is that we, after 2012, we discovered that GPUs do a lot of work and they can parallelize very well. They're good for math operations. And so that was one of the big reasons why deep learning took off, that compute became actually possible. So how has deep learning progressed? Basically, if you notice, in 2011, one of the big problems was image recognition, and image recognition was basically done with handcrafted networks, handcrafted priors, like you saw that there are kernels designed for edge detection, horizontal edge, vertical edge, slanting edges, all kinds of edges you have to detect. And by detecting those edges, you are able to do image classification. Now, before deep learning, the image classification error was very high, like 26% of the images were just misclassified. This is from ImageNet dataset. ImageNet dataset is a data set with 1 million total images, and ImageNet basically is one of the benchmark datasets which people use to test their image models. This 26% in 2011, then 2012, suddenly the drop was like 10% drop, and only 16% error rate in ImageNet in 2012. And then the error rate has continuously reduced. So the error rate is now just 3.1%. So that's a big achievement on the part of deep learning. And similarly, if you see question answering, then you notice that there is a huge jump in question answering when you go from, let's say, custom networks to BERT. And BERT based networks suddenly helped question answering models become really good. So let's get into what is a single layer perceptron, what is this basic building block of neural networks, and how does it work, how does it help us. Let's get into that. So what is a perceptron? So a perceptron is basically a single neuron, and it is inspired from biological neurons, wherein the idea is that a single neuron takes multiple inputs and then it is able to do something on those inputs, some kind of computation, and then give an output. So in here, what we do is an ANN is basically composed of multiple perceptrons, and you have multiple layers, each layer having some number of perceptrons, and finally the output layer gives out one single output, which is the learned representation that our perceptron has learned, our ANN has learned. Now let's dive a little deep into how each of these perceptron works and how the overall network is structured. So the network is divided into three parts actually. There is input layer, which is basically used for taking in all the inputs to the network. There are multiple hidden layers, which are basically stacks of perceptrons connected together. And finally, there is an output layer, which have one or maybe more than one outputs. And these outputs are used to do prediction or regression like tasks. And now, how does a single perceptron work? Like this is a single perceptron here. The whole image is a single perceptron, and each here in the previous slide, that is, each image here is a each node here is a single perceptron. So we are basically enlarging one node here and looking at it completely enlarged. So each perceptron basically takes in multiple inputs, right? For example, here it takes in 4 inputs, x1, x2, x3, x4, and it multiplies each of those inputs with a weight that is stored within the perceptron itself. And after multiplying the input with the weights, so w1 x1, w2 x2, w3 x3, w4 x4, it sums them up together, and after summing them up, it passes them through something called as activation function. So basically, we can write it in short mathematical notation as summation of wi xi, where I is from 1 to whatever number of inputs plus a bias term, and then pass through a activation function. That is the single perceptron and how it works. The parameters which a perceptron learns are these w1, w2, w3, and w4, which is learned during the training of the network. So we will take a small detour now, and we will look at some of the Python specifics that would be great to know. First thing we want to understand is vectorized implementation, or how does NumPy and vectors work. So in NumPy, you can define a vector by doing simply np.array and putting a sequence of numbers inside it, which is the vector. And if you do x, which is the vector here, x plus 3, then you simply get straight away all the elements of the vector being added, the number 3. So basically one operation, but it is vectorized or done over the entire vector, and that is a powerful way of using vectors in NumPy and Torch that helps us basically be able to kind of do the computations really fast without having to write our own for loops. We also talked something about activation functions just now. So basically, this function through which the summed inputs are passed in a perceptron, this G is called as an activation function. So what is this activation function? There are basically 2 or 3 activation functions. I'm going to discuss sigmoid first and then ReLU activation function. Sigmoid function is nothing but 1 by 1 plus e to the power in minus of input, right? 1 by 1 plus e to the power minus z. And the derivative is also very simple. The derivative of sigmoid is basically sigmoid into 1 minus sigmoid. So basically the derivative can be represented by the sigmoid function itself. How does it look like? So basically you can see that I have coded the sigmoid using numpy. So sigmoid is 1 by 1 plus e to the power minus z. And then I plot the sigmoid. This red curve shows you the sigmoid activation function, wherein if the input is less than 0, then the function's value is low, and if the input is really negative, then the function is 0. While if the input is more than 0, the function's value is above 0.5 here, and if the input is very high and positive, then the value is basically just 1. And then the derivative of sigmoid also, which was sigmoid into 1 minus sigmoid, that's the derivative here we have plotted in blue. And the derivative tells you that at very high or very low values, the derivative is basically 0, right? So in this region the derivative is 0, in this region also the derivative is 0. So this is sigmoid activation, and you can see how the sigmoid activation works here. You basically have our function that we defined earlier, and you can see that the sigmoid activation can be fed into it, and -3 gives a very small value while 0 gives 0.5. And similarly for the derivative also, at low values the derivative is very small, at very high values also the derivative is very small, but at 0 the derivative is 0.25. So sigmoid into 1 minus sigmoid is the derivative, right? And so a few factors to notice about the sigmoid derivative is that the derivative becomes 0 at both very high positive values and very negative values, very low negative values. So these factors cause problems in computing gradients, and as such there are few solutions called as ReLU and League-ReLU. So we will look at ReLU. So ReLU is nothing but max of 0 comma the input, and the derivative is 1 if the input is greater than 0. So basically something like this. The red line is ReLU. So basically ReLU was what? Max of 0 comma input. So when the input is, let's say, 5, then max of 0 comma 5 is 5. When the input is, let's say, 0.1, max of 0 comma 0.1 is 0.1. So above 0 it is simply a y equal to x line. Below 0, max of 0 comma any number negative is 0. So below 0, any input below 0 becomes just 0. That is the ReLU. And the derivative is 1 above 0 and 0 below 0. So since the derivative on one side does not become 0, the positive side derivative is not 0. So this ReLU activation avoids the vanishing gradient problem to a good extent. Now let's come back to our neural network and our perceptron and see how does it look for a bigger layer. So in case of a bigger layer here, we had seen one single perceptron, but here we are seeing 4 perceptrons together in a layer. How does it look for these 4 perceptrons, and do we like keep all these weights, W weights separately? How do we store them, and how do we do inputs to them? So we don't store the weights separately. We actually store all the 4 weights, all the 4 perceptrons weights in a single matrix. So here each perceptron has 3 connections, and there are 4 perceptrons. So the total number of weights will be 12. So we have basically a simple matrix which is 3 cross 12, and we use that matrix to store the weights. And again we will do a matrix multiplication to also process the input. So if the input is again here a matrix which is, let's say, n cross 3, like n number of inputs coming in, and each input has 3 numbers in it, n examples and 3 numbers in each example, then our input will be n cross 3 matrix. And then that n cross 3 matrix will be multiplied with this matrix, which is basically 3 cross 4, right? Here 4 perceptrons are there. So n cross 3 input matrix will be multiplied by 3 cross 4 weight matrix. So n cross 3 matrix multiplied by 3 cross 4 matrix will give us a n cross 4, right? So n cross 4 matrix will be our output from this layer. Now n cross 4 is what? Basically n number of examples, and each example having 4 outputs from each of the perceptron. So matrix multiplication can make sure that the whole layer with a big batch of inputs can be computed in a single multiplication. So here what we do is we train this network in this particular way and we forward propagate it. So each layer here will keep going ahead, like this layer gives 4 outputs, and in a batch of n it becomes n cross 4. Another layer will give some similar number of outputs which will be placed after this continuously like that, and once that whole thing is done you will get some output. Now how do we learn this network? How do we train this network, this multi-layer perceptron network that we have seen? How do we train it? So the training process is basically called as gradient descent, and gradient descent is nothing but it computes how much each of those weight parameters are contributing to the error of the network, to how much error the network is making overall, and then how much each parameter is contributing. That gradient descent tells us, and then we apply those values to each of the weights, and that process is called as back propagation, wherein each of the backward when we go to the backward pass we apply each of the weights this error correction that we found out from gradient descent. So the overall process is basically we define a model structure. We basically define the forward pass. We then implement something which can make predictions for us, the prediction routine, and then we also see how we can implement the cost functions. And in our case the cost functions are usually implemented in the framework and is very easy to implement, so it's not very hard for us to implement. And then we finally do gradient descent after each forward pass to see how we can update the weights of the network. Now one of the important things to note here is that we do not need to calculate the gradients. The PyTorch framework does it automatically for us, and a lot of other frameworks like MXNet, TensorFlow, they also do back propagation automatically for the programmer. You don't need to actually write the backward pass, you don't need to compute the derivatives yourself. So we do not need to compute the derivatives, but it is good to be aware of how the back propagation and the chain rule works. So we'll just breeze over the details very quickly, and then we will look at how the network is actually written in PyTorch. So basically what is back propagation, right? So we want to see that, like, if there is a simple function which is multiplying z by w3, z is our input, it is multiplying z by w3 and then doing a summation. So what is the derivative with respect to each of the variables, right? So the derivative of the whole function with respect to z is nothing but w3. Basically this we are doing derivative with respect to this, so only w3 remains, right? If we do derivative with respect to w3, then z remains, right? So the way that partial derivatives are computed is that you assume one of them as constant and the other one as a variable, and the one that you assumed as constant will become the partial derivative with respect to that variable, like here it has become, right? And in the similar way, if z is w1 plus w2, then the derivative is simply 1, because if you do derivative of w1 plus w2 with respect to w1, then this is constant and it becomes, the derivative becomes for this term 0 and from this term 1. So this is just basic derivatives, and then you come into something called as chain rule, right? So basically chain rule is helping you calculate derivatives for the hidden layers, for the inner layers of the multi-layer perceptron, or for an artificial neural network. How do you get the derivative of the inner layers? That is determined by using the chain rule. And the simple idea of chain rule is that if you have derivative of a function which is defined in terms of z, and z is defined in terms of w1, w2, w3. So how do you do derivative with respect to w1? So basically the function f is defined with respect to z, like f equal to let's say 2z, and then z is defined as a function of w1 plus w2. So z equal to w1 plus w2 and f equal to 2z. So how do you do a derivative of f with respect to w1? So that is defined by chain rule, and chain rule is nothing but simply you chain the derivatives together, d of f by d of f with respect to z and d of z with respect to w1 gives you d of f with respect to w1. So simply chaining the derivatives gets you the chain rule and helps us do within a neural network finding the derivatives from the middle layers. So we'll see a programmatic example of basically doing this derivative, and that will also show you how the framework actually takes care of this derivative work. So here we have two vectors. We are defining these vectors with PyTorch. So W1 is basically 0, 1, 2, 3, 4, 5, and W2 is the same. And we have a equation which is W1 square plus W2 cube. This 2 star operator is basically power operator. So W1 square plus W2 cube, and we call this backward method on this output, and then we can look at the gradients of the individual variables which went into this out. So W1's gradient will be what? W1 was W1 square, right? It is used as W1 square. So the gradient will be 2 into W1. And you can see that it's basically 0, 0, 1 is 2, 2 is getting multiplied by 2 again. Similarly here, so in this part, right, this entirely is for W1. So 2W1 is the gradient with respect to W1. Similarly, with respect to W2, what will be the gradient? W2 is cubed here. So W2 cube means you will get 3 into W2 square. So you can see that here we get similar thing. We get 3 W2 square, wherein for number 3 the gradient becomes 27. So here you can see how PyTorch calculates the backward gradients automatically, and you don't have to compute the gradients yourself. And this makes training neural networks very easy, because the error, the gradient with respect to the error that we need to update the weights gets computed automatically. So let's see how gradient descent helps us make these updates to the network and basically train the network. So what we do is we compute the loss first, and then we compute the derivative of the loss with respect to a weight. So whatever weights our network has, using the chain rule that we looked at earlier, we are able to compute the derivative of loss with respect to those weights. Now the derivative of loss with respect to those weights is nothing but how much those weights contribute to the error. So what we do is we change those weights and we subtract from those weights their contribution to the loss multiplied by a small parameter, which is the learning rate. So the learning rate is a hyperparameter which we adjust for different training algorithms and models, and it controls how fast the updates to the model are going to be. So in case of gradient descent, there are multiple types of gradient descent, like the stochastic gradient descent, wherein each update is done after running the model only on a single data point. Like if I have an image classifier, then I will run the image classifier on a single image, and then I will do the update, and that is stochastic gradient descent. On the other hand, mini batch gradient descent runs the model on a few examples and then does the gradient update or the learning. So for example, again in an image classifier, if you process let's say 32 images, and then based on the 32 images and their classification results, you see what was the loss and the error, and then update the weights, then that will be a mini batch gradient descent. On the other hand, the gradient descent algorithm, which is the gradient descent done on the entire training set, basically means that you will take all the images that you have available with yourself and run the model through all of them, and then compute the error and do the back propagation and update the weights. Now the problem with the gradient descent main algorithm is that sometimes the data set may be too large for you to fit the data in memory, and as such it's computationally not possible to do gradient descent itself. So we resort to either one of these, stochastic or mini batch gradient descent. So another thing is like in case of mini batch gradient descent, if you have, let's say, few examples like 10,000 examples, then, and each time you're doing each mini batch is basically 64 examples, then your overall training data set is divided into chunks of 64 examples each. And each time a chunk of 64 examples is passed through the model and their error is calculated, then the model weights will also be updated during training. So each of these small chunks is called as a mini batch. Now we discussed about that parameter called as learning rate, right, which is multiplied with the error contribution from the weight and then subtracted from the weight, right? So this small parameter is learning rate, and we want to see how its effect is, right? So for example, here I have taken a simple function which is described here using sinusoid and cosine functions, and then this is my final output. So final output is basically minus a into b, and a and b is defined as in 2D coordinates through a function of xy. Now we want to reach to the minimum point of this, and you can see that the minimum point of this is somewhere here, right? Somewhere here and here. So the correct way for gradient descent to do this is to basically just go here and stop here. But with a very high learning rate, it will keep bouncing around. With optimal learning rate only, it will reach here. So I have written a small function which basically helps us visualize this based on different gradient rates. So here you can see that the optimal learning rate gets it to the perfect position. On the other hand, if I have the learning rate too low, then it takes a lot of steps but does not reach anywhere because each step is very small. If the learning rate is too high, then it reaches the point and then bypasses that point. So it's kind of like this, wherein if the optimal learning rate is taken, then it reaches the right point. But if you are taking higher learning rate, then what will happen is that the model will reach here and then it will keep bouncing around from that same point. So we want to take a good learning rate and then only proceed. Another thing to note in these deep learning phenomena is that there are multiple minimas or multiple points to which the model can converge and show good results, and as such there is not one single minima, and it is also very hard to visualize a model's loss surface in a simple 2D plane because of having multiple minimas. So now we are going to get into the coding part and neural networks in PyTorch. In PyTorch, you can basically make a neural network by just doing nn.linear and then specifying how many inputs and how many perceptrons are there. And if you want a multi-layer perceptron ANN, then you can just put nn.sequential, and inside that you can put multiple nn.linear blocks, which are basically one layer. So this nn.linear describes one layer, and this describes a sequence of layers. And for training, as I showed you, that gradient descent requires learning rate, and you have to basically subtract the error contribution of each weight from itself in each step for updating. In case of PyTorch, you simply define an optimizer, and that optimizer will do it for you in every step. So I'll show you that also, how it is done. And we'll use a dummy data that I make here itself, and we will work on that. So some of the references that will come in handy, these two, deep learning with PyTorch in 60 minutes and PyTorch with examples, they are both from the PyTorch official library itself, and we can reference them later on also for our use. So let's prepare the data, and the data that I'm going to prepare is going to look something similar to this. So we basically prepare data, and we have basically used two features, the X and the Y coordinates, and the label is basically the color here. So the orange color is one label, and the blue and the green is a different label. We have also annotated them with numerical values here. The XY coordinates will be the inputs to the network. So for example, here the two coordinates which are like this, and for each coordinates there is a class. So we basically use that as the input to the network, and in general, following the good practices of machine learning, we divide our data set into training and test splits, where 25% will go into testing and 75% will be used for training. Next, we use PyTorch and make tensors out of these. Basically, tensors are like NumPy vectors, and they help us do computations faster. And then within PyTorch, there is a concept called a data set. So PyTorch datasets allow you to load data quickly into the model for training. So we define our dataset, and the dataset is composed of the input and the label. We have both train and test dataset here, and then we define something called as data loader in PyTorch. So data loader in PyTorch is basically helps us make a batch of data for doing mini batch gradient descent. So these data loaders help us make one batch of data, and then keep looping over the overall data set in batch wise fashion, and then train our network. So we also make train and test data loaders. Next, we define some helper functions. So a few of the helper functions that we will need is one, to evaluate the accuracy. This helper function helps us evaluate how good our network is doing. Then we have another helper function for making the predictions, and another helper function for plotting the decision boundary. So using these helper functions, we will be able to basically visualize how our network is doing as well. And next, we'll look at how we build our network. So one of the things you want to do is you want to do weight initialization, and you want to build your network after that. So how to build your network? This function here, this is going to help us build our network. So the function takes a name, how many number of inputs are going to come. In our case, that is 2. Number of outputs, that is just 1. And the number of layers that we want to use, hidden layers, and some other parameters that we'll discuss later. So as we initially discussed in PyTorch introduction, so we define each layer as nn.linear block. So some number of inputs and some number of outputs, and then finally we put all the layers into a nn.sequential block to make multi-layer perceptrons. This for loop here helps us just build each layer based on the specification. So finally, we look at how to train the network, and what is the function to train the network. And in this, the main things are here. So first thing is the loss function, right? So how do you compute the loss once the network gives you the output? So cross entropy loss helps us do that. Similarly, we also want to see how the training loop works. So if I want to make 10 passes over the total data set, then I will have epochs equal to 10. So that is passed as a parameter to the training function. And in each epoch, I will basically go through the training data within this for loop. Basically, I'll go through the training data. I will then put the training data to the required device if I have a GPU. The training data will be passed to the network, and an output will be obtained, which will be the class label. Then this output will be basically passed to the cross entropy loss function to get the loss. We will call the backward method on the loss function, and this will compute the gradients with respect to each of the network weights. And then the optimizer that we talked about, the SGD or any other optimizer, which is helping us compute the updates. So based on the learning rate and the computed loss, the optimizer will update the parameters directly. So all this is done automatically, and the whole network training happens in these few lines of code itself. The remaining code is mostly for helping us visualize the loss and print out the loss, and for doing training over multiple epochs. But the main part happens in only few lines, and that helps us train the network. So I will define a basic network here. I have defined one basic network here, and this basic network basically is just having 32 perceptrons per layer and just one hidden layer. And I will see how the accuracy is. So this network is being trained for 24 epochs. So we are able to reach 76% on training again. So the accuracy varies between 73 and 76 for this. And you can see that the network was still doing further better and better. Like we could have trained for a little longer, I think. And yeah, this is how the boundary looks like. So let me make some changes to the network and see how it does. So one of the changes that we will make, so some of the tricks that we can use to improve the performance, we can train it a little bit longer. So let's try training for 50, I guess, instead of 25, so twice longer. All right, so for by training for longer, we are able to reach around 89% accuracy, and the boundary also looks much different now. The classes which are together have been classified well. Only here you can see that there is a mistake that is happening in this part. So we'll see if some other tips and tricks can also help us do better, and we'll go through those. So some of the other tips and techniques that we use to increase performance are like we can adjust a neural network architecture. For example, I can actually take 128 perceptrons in each hidden layer, and I can also increase the number of hidden layers themselves. And using this, we can notice that our network is now able to get an accuracy of 95% in train and 94% in testing. So it produces a boundary which looks like this, which is able to do classification of these points much better. Similarly, there are few other techniques like better optimizers which use momentum and adaptive estimations. So for example, a momentum optimizer that we describe here basically computes momentum over multiple steps, and the momentum that is computed helps the optimizer to basically get over local minimas and saddle points. So for example, here you can see that optimizers with no momentum will basically get stuck in this saddle point, but optimizers with momentum can go down this saddle point and reach a better minima. So that is one of the ways that new and better optimizers work. For example, momentum, which is this orange line, finally goes down. On the other hand, optimizers like Adam and Adagrad are very quick to basically figure out that they need to follow this direction. For example, Adam and Adagrad immediately followed this direction. So better optimizers also help. Gradient descent just simply gets stuck, so it does not move and plain gradient descent. So we will also try to use momentum and see how it does. So here I have taken the same configuration as the last time in which we had a bigger network, but here we also add a momentum parameter. So with momentum parameter, we notice that our test accuracy is no longer 94.2% like it was before, but now it is 97.4%. So if you remember, let me take you back. Here the test accuracy is 94.2 and there is no momentum, but everything else is same. Then here with momentum, we are able to get 97.4%. So momentum is one of the very good techniques, and it produces also better class boundaries, which do not look as jagged as the previous, just increasing the network size. Then there is another technique called adaptive moment estimation. So adaptive moment estimation basically estimates the momentum itself in each step and applies some corrections which enable us to get a better view of the momentum parameter itself. And based on that, it updates the weights for each of the weight. For every weight, the adaptive moment estimation is done, and that's why the Adam algorithm that is here works very well. So here you can notice that we are also trying Adam, a variant of Adam, which is referred to as Adam W in PyTorch. We don't get a lot of improvement over the vanilla network, but we can see that there is some difference. And the loss surface looks very good, but the overall improvement is not happening very well because of few misclassifications here. Finally, we come to a regularization technique. So dropout regularization is basically a way to regularize your neural networks, wherein if the neural network is too deep and too large, then it will start memorizing the data. So what we do in dropout is basically we simply drop some neurons every time we do the forward pass, and we use only few neurons instead of using all of them. This results in the network trying to learn how to do predictions despite having some of the inputs missing. For example, this neuron here is not able to get input from this 3 neurons in the previous layer, right? So because of that, it has to learn how to do predictions despite these neurons not being present. And that regularization helps improve the performance of the network, as well as prevent the network from remembering the data just without understanding anything. So with regularization, you can see that we don't use any momentum, but with dropout regularization, you can see that our performance is very close to the best network that we have seen till now. Then we adjust the value of dropout a little bit, and we can see that the dropout value after being adjusted, even with a single layer network, is able to give us 99.2% accuracy on this data set. So what does this tell us? And let's just look at the dropouts classification visualization, and you can see that the dropouts classification visualization is also very smooth, and it looks intuitive from our perspective of how we would have done it in a possible way, right? So the dropouts advantages are multiple, and the dropout regularization actually took our network to the maximum possible accuracy, 99.2%, right? So Essentially, you can notice that dropout is one of the most important tools when you're trying to get high performance from the network itself. There are many other techniques to tie as well. There are things like hyperparameter search, wherein you will try to see which value of learning rate, momentum, and number of layers works better by doing a search over all of their combinations. There is batch norm and layer norm, which is basically a way to normalize the network between different layers and ensuring that you don't have problems like vanishing gradient because of high values of activations. There are also better network initialization. For example, here you can see that initialization plays an important role, right? If your network is initialized at the right point, then it can reach the minimum of the possible error, right? So the minima can be reached, we can get the lowest possible error. But if it is initialized in a point which is not good, then it will just not reach the minimum error itself. So good initialization is also important. So these are some of the techniques to try. Up next, we will actually look at convolutional neural networks, which are used for image processing and for image recognition, semantic segmentation, and many other image related problems. And after that, we will look at sequential data like text, how to handle that with recurrent neural networks. And after that, we will have a Q&A session. So feel free to ask any questions in the Q&A session, and we will be live in that session, present to answer any of your questions. Thanks for attending this session.
Hi everyone, welcome to the ML Summer School's module on convolutional neural networks. I'm Nikita Prabhu, an applied scientist with the India Machine Learning team, and I'll be leading you through today's session. These are a few key takeaways from this session. We will begin by looking at a few applications of CNNs. Where are CNNs used? And then we will move on to why we need CNNs. So you already learned about MLPs. So why can't we just use MLPs? What is the need for a special architecture called CNN? Next, we will try to understand the different components you'll usually find in the convolutional neural network and what each of them do. And well, then next we'll learn about, next we'll take a look at what CNNs really learn, and followed by looking at a few popular CNN architectures. Finally, we'll look at a few tips and tricks to train CNNs, and then we'll move on to the lab session. So let's begin. Where are CNNs used? CNNs are architectures of choice when dealing with images and videos. So any computer vision related task that you see, like face detection, person tracking, object recognition, is likely to be using a CNN backbone. You'll already have used some of these. For example, when you take a picture on your smartphone, it generally shows you a box around people's faces. That's face recognition. Right? If you've used Amazon AWS, you might have come across the service recognition. It's a service that makes it easy to add image and video analysis to your applications. You just provide an image or video to the recognition API, and it can do a number of things like, detect objects in the image, recognize faces, text in the image, do tracking of people. So it can also flag inappropriate content. It's a highly scalable deep learning technology that leverages CNN architectures in the backend and has been developed by our computer vision scientists to analyze billions of images and videos daily. Another place where you can see CNN at work is in visual recommendation. So if you've been to the Zappos store, which is the clothing and shoe retailer owned by Amazon, it has a widget that provides visually similar recommendations. So this is the product that you're looking at and gives you visually similar recommendations. And this engine is powered by CNNs. And the application that you can see is to detect defects, right? So we have a huge catalog of products at Amazon containing billions of images, and there are some guidelines that we expect from we expect sellers to follow when uploading these images. So, for example, this is an ideal image. These images are defective images. So this image does not have the required white background. This image has a mannequin instead of a real person, and in this image, the model is not standing. So we need to be able to enforce these and these requirements. And one option is to do a kind of manual check on each batch of images that are uploaded. The other option is to have an automated system to do this for us. Right? Obviously, the later option is more efficient. So we have a CNN-based model that is triggered every time a seller uploads an image, and the model validates it and flags out the ones which are violating the guidelines. So now we have seen a few applications of CNN. Let's go to the next step and see why do we need CNNs to deal with these sort of applications. Recently, there has been a lot of progress made in understanding images. Let's consider the problem of image classification. In image classification, you have an input image. In this case, it's a cat image, which we feed to the image classifier. And the classifier should give you the probabilities of that image belonging to several different classes. Here, there's an example. In this example, we have these 4 classes, but generally you have a lot more classes, right? And this image classifier in this case says it's a cat with a probability of 91%. So in classical machine learning, what was the approach to deal with this sort of problem? It was generally a two-stage approach. The first stage was feature extraction, where from the image you extracted certain useful features, such as SIFT or HOG, this scale invariant feature transform or histogram of oriented gradients. These features were then passed into a classification module, and the classification module gave you the probabilities of the different classes. However, this is not the most efficient method, and since the features are actually handcrafted, and accuracies were not really very high with these kind of methods. Then suddenly, a few years back, deep learning came into the picture and revolutionized the computer vision field. Neural networks took out the first task of feature extraction from our hands. These networks have the ability to jointly learn the features while at the same time performing the classification task. So these neural networks need a lot of data to do this. You've already learned about fully connected networks in the previous session on MLPs. So how does the architecture of a fully connected network look? You have input layers where you're going to feed in the input vector. You have one or more hidden layers, and then you have the output layer, and the size of the output layer depends on the number of classes you want to have, right? Number of classes you want to classify into. So, and each of these layers are connected to every neuron in the preceding and succeeding layer. So, image is nothing but a matrix of numbers, right? Or when you can also, it's a pixel values. So we can convert this 2D matrix into a 1D vector. This process is called flattening the matrix. And you can feed this flattened matrix into the MLP. Now let's look at the number of parameters required to do this, right? So let's consider a small image, an image of 40 cross 40 cross 3. 3 is the number of channels. And you're classifying it into just 4 classes. So your number of outputs is 4. And you don't have a hidden layer. So you just have an input layer directly connected to the output layer. What is the number of parameters that the neural network will have? Okay, the number of parameters will be 40 into 40 into 3 into the number of outputs 4, which will be approximately 20,000 parameters. So for a small image, this is a rather lot of parameters. Let's add a hidden layer of size 100. If you add a hidden layer of size 100, number of parameters now increases drastically to 480,400. So we're still processing a rather small image. What happens if you increase the size of the image and also increase the number of object classes you want to classify into? ImageNet is a very popular database, an open source database which is used in the ILSTRC competition, which is held annually. And it has 1,000 different classes of objects. rather than large training set of 1.2 million and 100K test set. Now consider classifying on this database. You have images of size 200 cross 200 cross 3, 1000 dimensional output, and you're going to use a single hidden layer of 4096 dimensions. For such a data set and an architecture, number of parameters you'll require in an MLP is 495 million, which is huge. And most often, a single hidden layer will not suffice. You will need multiple hidden layers to get good accuracies. So one of the problems of using MLPs to deal with images is a large number of parameters these MLPs require when coming to process images. And as the number of parameters increase to prevent overfitting, you need more data as well. So this is a problem. The other issue in using MLPs to deal with image data is that MLPs completely ignore the spatial structure of the images. So image is a 2D matrix, and to feed it into MLPs, you need to flatten it into a 1D structure, thereby losing all the spatial information. So these are the two problems of using MLPs for images. First, the number of parameters blow up exponentially. Second, we lose spatial information present in the image. So what's the solution? The solution is to use a CNN. Over the next part of the lecture, we will see how CNNs were able to overcome these limitations. But first, let me just give you some history of CNNs. The first CNN model that was used in practice is Linnet, which was proposed by Jan LeCun, who is considered the founding father of convnets. He was able to successfully develop this architecture and use it for recognizing handwritten digits on US checks. Then in 2012, Alex Krzyzewski proposed the AlexNet. This is the first large-scale CNN which was able to do well in the ImageNet or ILSVRC competition. This architecture was able to beat the traditional models by a huge margin at that time. And this network triggered a lot of interest in the community, the CV community, and started a spree of research in the field of CNNs. So as you can see, these networks directly take in 2D images. There is no need to flatten the matrix into a vector before feeding it into these models, and therefore they are able to preserve and take advantage of the spatial structure present in the images. Now let's look at the building blocks of CNNs. These are the building blocks of CNNs. CNNs are very similar to ordinary neural networks in the sense that they are made of neurons with learnable weights and biases. Each neuron receives some inputs, performs a dot product, and optionally it is followed by a nonlinearity. The output layer still has probability scores for each class in the case of classifier. But the difference in CNNs is that unlike in regular neural networks where neurons are arranged in 1D, in convnets, neurons are arranged in 3 dimensions. So the input image will have 3 dimensions: width, height, and depth. And the neurons in a layer will not be connected to all the neurons in the previous layer. Instead, it will be connected to a small region in the previous layer when the convolution is taking place. So we'll look at each of these layers now in a little more detail. First, let's take a look at the input image. So in the image classification scenario, the input to the CNN is an image, an RGB image, or which is what is called in local common parlance as a color image. Right? It has 3 dimensions: height, width, and number of channels. And in RGB image, number of channels will be 3: red, green, and blue. Now, the most important block of CNNs, convolution. So what is convolution? Convolution refers to the process of sliding a block of numerical values called the kernel or the filter over the image and taking dot products at each step. So you have this filter of dimension 3 cross 3, and you have an image of dimension 7 cross 7. Okay, so you're going to take this filter, place it over the first 9 pixels of the image, and you're going to take a dot product, which will give you the result 1. You're going to slide the filter by 1 pixel each in the horizontal direction first, take a dot product, which will give you 4, and slide it again, take the dot product, which will give you 3. Once you reach the end of the horizontal strides, you come down and down by 1 pixel, and again take a dot product to get 1, and then 2, and so on. So suppose you have a input image of 32 cross 32 cross 3. Your filter will be of the size 5 cross 5 cross 3. And the depth of the filter usually matches the number of channels in the input. Okay. So you perform the convolution. At each location, you multiply all the elements of the filter with the elements of the corresponding elements at the location at which the filter is placed in the image, and you get a single output. This output will form a part of your output activation map. Okay, so you take the filter, slide it all over the image step by step, and each dot product output that you get is placed in the activation map, and this is your output of the convolution. Okay, so what would be the dimensions of this output? The filter size is 32 cross 32. Sorry, the image size is 32 cross 32 cross 3. The filter size is 5 cross 5 cross 3. The dimension of the output will be 32 minus 5 plus 1, which is 28 cross 28. And the depth of the output will be 1, since both the filter and the image have the same number of channels. So if you have one filter, you will get a 2D activation map as your output. But generally, more than one filter is used for convolution. In this case, you have 6 separate activation maps produced by 6 different filters, 6 different 5 cross 5 filters. Okay, a group of filters are usually called a filter bank, and the weights of these filters are learned during training, just as the weights of the MLP were learned during training. So to recap convolution, you have an input image, a 3-dimensional input image. You have 3-dimensional filters, and a set of filters forms a filter bank. Each of these filters operates over the image by sliding over it, and at each position of the image, it convolves or takes a dot product with that portion of the image and gives you an output. So finally, you get a block of activation maps. So the output of convolution is called an activation map. You get a block of activation maps. All right. So these filters extract features from images, and these features are then used to do the classification. So how are these filters different from the weights you train in MLPs? A couple of things. One thing, the filter acts in a local area. It does not look at the entire image at once. It looks at a local area. And the same weight of the filters are used to operate all over the different regions of the image. Okay. So this operation on local area allows the filter to take advantage of the spatial structure present in the image. And also, because the same weights are used throughout, this leads to translation invariance. So why is that useful? So consider you're trying to look for a cat in an image. The cat can be present anywhere in the image, and you want to find the object irrespective of where it is. So the filter should act the same in all when looking at all different regions of the image in order to find the cat. The next block is nonlinearity. So you will already have come across some nonlinearity in your MLP session. So sigmoid and tanh are something that you might have come across. So these are two S-shaped nonlinearities. Sigmoid ranges between 0 and 1, and tanh ranges between -1 and +1. So one of the problems with these two nonlinearities is that they saturate in certain regions of the input. And saturation leads to problems like vanishing gradient when you're doing gradient descent. These are not very commonly used, as this vanishing gradient problem leads to slow convergence. Another popular nonlinearity is a ReLU nonlinearity, which is simply the max of 0, the input. Right. So in the negative axis, it is just 0, and the positive axis is a linear curve. It's a straight line. So this non-linearity leads to faster convergence. But again, you can see that this also saturates in the negative region. So there are a few improvements that have been introduced over this, like parametric ReLU and leaky ReLU, which gives it a small slope in the negative axis as well. So if you go to any package which implements CNNs, you can find a number of non-linearities other than these as well, and you can look at them and decide this is the best one for your network. The next block is spatial pooling. So what does pooling do? Suppose this is your input, 4 cross 4 dimensional input, and you have a max pool filter of size 2 cross 2. Okay, so you're going to have a max pool filter of size 2 cross 2. And you're going to move with the stride of 2. What does moving with the stride of 2 mean? Earlier, when you were moving along the image, either in the horizontal or the vertical direction, you were moving, each time you were moving by 1 pixel. If you have a stride of 2, it means you move by 2 pixels instead of 1. Stride of 3 will mean by moving by 3 pixels in both directions, horizontal as well as vertical. Now let's look at the max pool filter. So you're going to first look at the first 4 pixels, since the max pool has a size of 2 cross 2, and you're going to pick the maximum value among these 4 pixels. So in this case, it's 6, and that's going to be output. Now you move with the stride of 2. So 1 and 2, you reach these 4 pixels, pick the maximum value, 8, move vertically by 2 pixels, and you come to this block, max of 3, and here the max is again 4. Right, so this is your output. So you can see that max pooling reduces the dimension of the output. So if you have a image block of 224 plus 224 with 64 channels, pooling will reduce dimension to 112 plus 112 plus 64. All right. So max pooling operates over each activation map independently, and the pooling layer, the main advantage of reducing spatial dimension is that by having lesser spatial dimensions, you need to have lesser parameters, and this reduces the chances of overfitting. So what is the use of max pooling? Max pooling makes the models invariant to small shifts and rotations in the object, invariant to small interclass differences. The intuition is that the exact location of a feature is less important than its rough location relative to other features. Max pooling also allows that particular filter to have a larger receptive field. What is the receptive field of a filter? It is the area or the size of the region in the input that produces a particular feature. Now we can look at the fully connected layers. This is something that you've come across already in the MLPs. So you have the final convolution activation maps, 3-dimensional, which you flatten to get 1D output, and that is passed on to the fully connected layer. So what are the advantages of fully connected layers? This has a global receptive field. These fully connected layers look over the entire image and produce an output. And these layers are connected to all activations in the previous layer. Finally, we come to the classifier. So in our case, we are using the softmax function as our classifier. So what is a softmax function? Softmax function takes an n-dimensional vector of real numbers and transforms it into a vector of real numbers in the range of 0 to 1, which add up to 1. In other words, it converts your scores, whatever scores your CNN or fully connected layers have given, into probabilities. So as the name suggests, softmax function is a soft version of the max function. Instead of selecting one maximum value, it breaks the whole one with the maximal element getting the largest proportion of the distribution, but all the other smaller elements getting some of the distribution as well. So to get the entire architecture of the CNNs, you stack multiple layers of convolution, non-linearity, and pooling together. Right? For example, this particular block has all 3: convolution, non-linearity, followed by pooling, which you can see because the dimension of the next layer has reduced. This is because you have a pooling here. And then again, another block of convolution, max pooling, non-linearity, and max pooling, and another, and finally 3 fully connected layers. Similarly, in AlexNet, this is Linet. Similarly, in AlexNet, you have 1, 2, 3, and 4, and 5 convolutional nonlinearity and pooling blocks, followed by 3 fully connected layers. Okay, now we know how CNNs, what are the blocks, different blocks in CNNs, and what each of them do. But what kind of features do these CNNs actually learn? These are some of the features that are actually learned by CNNs. So the first few convolutional blocks learn very low-level features like edges of different orientations and color blobs. The subsequent filters learn slightly more complex patterns, right? So they learn things like grid-like structures, concentric circles, and so on. And as you go deeper and deeper into the network, the filters learn increasingly complex patterns. So you can see here a honeycomb-like structure, something like a face, an eye. And if you have a really deep network, the final layers are even able to capture object representations. Now let's look at a few popular CNN architectures. This is the results of ILSPRC competition over the years. These are during 2010 and 2011. CNNs were not used. These are just shallow networks, traditional shallow networks, and this is the error rate. You can see that as time passed and deeper and deeper CNN networks were introduced, the errors rates have fallen drastically. So this is the architecture of AlexNet. AlexNet has 8 layers, as we've previously seen, 5 con and 3 FC layers. The first con layer is of dimension 11 cross 11 with 96 filters and a stride of 4 and a pool size of 3 cross 3 with a stride of 2. Then you have a bank of 5 cross 5 filters, 256 5 cross 5 filters, followed by 3 banks of 3 cross 3 convolutional filters. And this is GoogleNet. In GoogleNet, you have a new module which is introduced called the inception module. So the inception module, instead of extracting features at a single scale using a single set of filters as an AlexNet, for example, here 11 cross 11 filter is used and then 5 cross 5 filter is used and so on. In GoogleNet inception module, at a time you use filters of different dimensions. Here you have 1 cross 1 convolution, 3 cross 3 convolution, 5 cross 5 convolution, 3 cross 3 max pooling, all done on the same set of input. The outputs are then concatenated and passed to the next layer. So this was to introduce multi-scale computation to extract features at multiple different scales. So GoogleNet composes largely of these inception modules along with some other layers, just like SimpleCon, to give the entire network. GoogleNet was able to get a good accuracy improvement over the previous year's ILSPRC. A couple of other popular CNN structures, ResNet. So before the introduction of ResNet, very deep networks were hard to train because of the vanishing gradient problem. So as the gradient is propagated from the final layer back to the earlier layers, repeated multiplication made the gradient infinitively small. As a result, as the network went deeper, its performance got saturated or even started degrading. ResNet introduced residual connections or skip connections, right? So these connections skipped a few blocks. So you can see that it's not connected to this block, right? It skips a few blocks. And this allowed the network to learn better. So the authors hypothesized that residues would be easier to learn than the entire function, right? So the outputs of this particular layer were directly added to the input, to the output of this layer, and it is totally the sum was passed to the next layer, right? So this layer only needed to learn the residues. So this architecture allowed the authors to train a 150 layer network and win ILSPRC 15. DenseNet is another network that further exploits the effect of shortcut connections. It connects all layers directly with each other. So every layer is connected to every other layer. So the outputs of each in this architecture, the input of each layer consists of the feature maps of all earlier layers, and output is passed to each subsequent layer. The feature maps are aggregated with depth concatenation. Each layer receives the collective knowledge from all preceding layers. So now let's quickly look at how to train CNNs. Suppose you have a small set of images which is not enough to train a model, say 100 cat images and 100 dog images, which is not enough for model training. What do? You can augment data set. So data augmentation is a way of increasing the number of images you have in the training data. So let's say you have an image of a cat, and what can we do to do data augmentation? You can flip the image and therefore get two images. You can crop the image, take different portions of the image. You can also rotate or translate the image. So all these different samples that you obtain by doing these different operations can be added to the training data with the same label. So you can drastically increase the size of your training data. Some other things to keep in mind while training CNNs is you need to choose the right optimizers. Stochastic gradient descent is one thing you know. There are also other optimizers like ADAM and ADAGRAD. You need to set the right number of mini batch. These are some things that come by experience, which is the best optimizer, which is the right set of mini batch to use for your particular problem. What are the issues that come up? Exploring and vanishing gradients. We have discussed a little bit about vanishing gradients and the ways to get over it. Residual connections is one. Exploring gradients you can get over by doing gradient clipping. And you also need to think about the right initialization to use for your weights and the right activation functions to use. And the problem is overfitting. This you can deal with by the regular ways of adding L1 and L2 regularization to your loss function, increasing the data by data augmentation. And another neural network specific way is dropout, where you randomly drop neurons during training. This gives it an ensemble-like effect and helps overcome overfitting. So the other thing is transfer learning. So when you train your neural networks, you have to initialize the weights. One way to do it is to initialize the weights by randomly, or one of the initialization methods of Xavier MSRA, and then train the neural network for your particular task. This is called training from scratch. The other more commonly used way is to take the weights of a trained network. So the lot of trained networks are available, AlexNet, GoogleNet, ResNet. These networks are trained on large data sets, and these trained weights can directly be used in your network. So you initialize your network with these trained weights, and then just train the last few layers for your task. Okay, suppose AlexNet, AlexNet trained on ImageNet has 1,000 dimension layer at the end, and if your classification requirement is just 500 classes, you can remove this last layer, replace it with a 500 dimensional layer, and just retrain this last few layers. This is called fine-tuning the model. So these are some of the key ideas we have learned today about CNN. Local connections, allowing it to take advantage of the spatial structure and introduce translation invariance, pooling to reduce dimensions, hierarchical features. The first few layers learn basic features like edges and blobs, and then you go on to more complex features, and joint learning. So these neural networks are end-to-end models where you learn both the features as well as the task which you're trying to perform. Let's now go to the lab section. In the lab section, you're going to do image classification on a database called SIPA10. It has around 60,000 32 to 32 RGB images, which you'll be learning to classify into 10 classes. These are the 10 classes given here. So let's open the Jupyter notebook that's been shared with you. This has a lab session. The packages that need to be installed are NumPy, Matplotlib, PyTorch, and TorchV. If you have these packages, you should be able to run this notebook. So as I just mentioned, we'll be doing a classification on the SIPA dataset, right? So we will be loading the SIPA10 training and test datasets using Torch Vision, defining a convolutional neural network, a loss function, and then training the network on the training data and evaluating the trained model on the test data. So let's first import the required packages. And then let's load the dataset. So Torch, we'll be using PyTorch for this exercise, and Torch has some easy ways to load the popular datasets. Its dataset module allows you to directly load the CIFAR 10 dataset and create a data loader. A data loader is a module which helps you take the train or test dataset and select an appropriate batch size, select if you want to shuffle the data or not, and then it provides you the dataset for each batch. So it's downloading and verifying the images. Now let's plot a few images and take a look at the data. So we'll be plotting 4 images, okay? A ship, a horse, a car, and a bird. So you can see that, there's a little pixelation because these images are really small, 32 by 32 images. Let's now define the convolutional neural network. So we're defining a simple network with 2 conv layers, a pool layer between them, followed by 3 FCs, right? So the syntax is like this. The first element here, 3, is the number of input channels, which is, since you have an RGB image, number of channels is 3. The number of output channels is 6, and the filter size is 5 cross 5. Okay. Similarly, here for max pool, the kernel size is 2 cross 2 and stride used is 2. And the final number of classes that you have, the output dimension is 10. So you define the column layer, you also define the forward function, where you pass the input into each of these layers successively and get the final output out of the final layer. Okay. Now we are going to define the optimizer and the loss criteria. Since we're doing a classification, we are going to use the cross entropy loss. It's again very conveniently accessible in PyTorch. So I'm going to define my loss criterion as cross entropy loss. And I'm going to use the simplest optimizer, STD, as my optimizer. Now let's do the actual training. So how we're going to do this? We're going to loop over the dataset multiple times. Each iteration over the entire dataset is called an epoch, and we are going to have 2 epochs. Generally, you train a little longer. But for this simple problem, 2 epochs is sufficient. Then you loop over, in each epoch, you loop over the entire data using your train data loader. So the train data loader gives you the data, you split it into inputs and labels, and then you pass those inputs to your net. The net is nothing but the neural network we defined a few steps back. Okay, and you get the outputs. These outputs are passed along with the labels to the loss function, which gives you the loss. The loss is then you lost or backward. The step calculates the gradients of all the weights with respect to the gradient of the loss with respect to all the different weights, and the optimizer or step does the actual weight update. And this is just some code to print the loss after every 2000 mini batches, right? So let's wait for the training to get over. You can see the loss being printed. So you can see the loss is falling as the number of epochs proceed, as the training proceeds. So when the training is going on, let's look at the next step. So you're going to save the model here. Okay, and then you're going to test the model on the test data. You can see the loss falling. You have finished 1 epoch here, right? You have 1 more epoch to go. So now we are saving the model, and after saving the model, we are going to load the test data set, again using the data loader, and we are going to display a few images in the test data set. And after that, we are going to load the saved model uh, using this load state def function of PyTorch. And then we're just going to pass the test data. We're going to just take 4 images which were loaded using test data and pass it to the model to see what the outputs are. Okay. So what we're predicting is the probability for each of the classes, and we're going to pick the maximum probability for as a final output. So the results seem pretty good. It's able to recognize cat, ship, car, and I think car is wrong, but again, this looks like a plane. I'm not sure. Okay. So now let's look how it performs in the entire data set. We are going to pass the entire test set batch by batch into the network and look at the outputs and calculate the accuracy and also the class-wise accuracy. So the accuracy over 10,000 test images is 53%. And now let's look at the class-wise accuracy. So 53% is pretty good since since you have 10 classes, if you pick randomly, you're going to get an accuracy of 10%. 50% is not bad. And then you have the class-wise accuracy. You can see that it does best for truck and worst for cat. So these are some of the references we used during the session. And hope you've all been able to learn in depth about CNNs from this session. We will now take a break and return with the RNN session, following which we will have an interactive Q&A.
Hi, welcome to part 3 of Deep Neural Networks, which is the second session of Machine Learning Summer School by Amazon India. I am Faizan, your tutor in this session, and I'll be walking you through what are recurrent neural networks and why we use them. So in this session, we will cover all the details about recurrent neural networks, like what is a vanilla RNN, recurrent neural network, what is its structure, and how is it trained. We'll also see some of the challenges facing these type of networks and how are such challenges alleviated from these networks using something called as LSTM and something called as transformers. Finally, at the end of this session, we will go through a exercise video, which will be a small lab, and we'll see some code examples in that. In the first session on multi-layer perceptrons, we actually talked about something called priors or inductive biases. So in here, what I mean by inductive biases is that what kind of structure is our model encoding in the network itself, which takes some advantage of the data. For example, you can see that in case of convolutional neural networks, the nearby pixels have more say in what the convolution will output than pixels which are farther away. So in a similar way, what kind of biases are taken into account in our model so that it can do well on a given task? For example, in case of recurrent neural networks, we assume that any data that came just before the current time step or any data that comes right after the current time step is more important for making a decision at this point in time. Or you can also say that another inductive bias is that we use word as a uh, complete token or as a token in NLP, but we don't use characters very frequently. We don't use alphabets or characters very frequently, but we rather take the whole word, and that word forms the unit, like one pixel. A word forms one unit in NLP. So we discussed about how RNNs and CNNs have some kind of structure in their data, and these exploit this structure. So what kind of structure does RNN exploit, or what kind of data do we feed into RNNs? So we basically feed sequential data into RNNs, and sequential data is nothing but something like a sentence which is having a sequence, and the main idea is that the words which come close together are more relevant to the meaning of each other than words which are very far away, and we read them up also left to right or right to left and in a sequence, right? Similarly, speech also is a sequence, and videos are also sequence. We have a past, present, and future in each of these elements, and there is a time dimension. So all this sequential data is what an RNN helps us to model. Now, humans, how do you understand sequence? We basically understand a sequence by remembering what has happened in the past. So we use the past to understand, and these RNNs, they also have something called as memory. The RNN actually uses this memory internally, and it uses this memory to basically store what has happened in the past and keep some context of the past and use that to make sense of whatever data comes out of the current time step. So we also want to see what are some of the applications of RNN before we go deep into why an RNN is required. So some of the applications of RNN are speech recognition. Basically, whenever you call to the Alexa device and ask it a question, that gets transcribed into text through an RNN, and then again the response is sent back to you. Similarly, machine translation, wherein Google Translate or Amazon also translating one page which is written in English to a different language. All those are machine translation, also depends on RNN. So there are a lot of applications of RNN. Question answering is also an application, like if you have a question, then an automated RNN can read the question and then answer it based on the product details. So how does an RNN differ from a multilayer perceptron or a CNN? So in case of multilayer perceptrons and CNNs, there is a single input and the network is one network and it processes and gives one output, like classification result of whether an image contains a cat or a dog or not. And also similarly classification results for tabular data and other things. But in case of RNN, there could be multiple variations. Like for example, it could be one to many, like for example, videos or for example, translations. It could be many to one, like sentiment analysis. It could also be many to many, and it could also be many to many in a little different form, which is direct generation. So let's talk about one application like many to one. Sentiment analysis, which takes in a sequence of words and then tries to make some sense of what the overall sentence is, like is it expressing happiness, sadness, or is it expressing some dissatisfaction in the product that has been sent out to the customer in the review. All that comes under the sentiment analysis, wherein we are looking for just one output, which is the sentiment of the sentence. Movie reviews and IMDb reviews also would come into the same place, and they also have been classified into positive or negative. Similarly, there can be one to many also, like for example, if you have an image and that image needs to have a caption and you are using a RNN to generate caption from an image. Then for example, this image here, you would want a caption which says black and white dog jumps over the bar. This is a pretty appropriate caption, and it would basically use an RNN inside which takes the image and then generates the caption. Similarly, there could be applications wherein it is many to many. For example, machine translation is a direct example of that, wherein it takes a sequence in one language and then outputs it in different language. Similarly, there could be another application of many to many, which is a little different from the previous one. Here, what happens is that you have a frame coming in, which is, let's say, a game of football, and you have the ball here and some players chasing the ball. You may want to annotate where the ball is and who is chasing after it. So that kind of processing would basically also be a many to many processing, but it will be done frame by frame. So you don't wait till the end result and do it. Like in this case here, you don't wait for the end result and do it. You do it directly right after that frame itself. But you also keep some historical context for helping in detecting the ball. For example, here the ball is pretty blurry. A previous frame could help us determine that this ball was kicked by this guy. So let's look at how the RNN actually works and what the RNN exactly does internally. So RNN is usually nothing but a equation which combines three weight parameters, and we had discussed how these weights are multiplied with inputs to give some result in the multilayer perceptron section. Here I want to basically kind of give you one important idea about RNN and about any deep learning model, for example, right? So what happens is PyTorch or any framework like TensorFlow, these frameworks can compute the backward gradients if you are able to write the forward propagation, right? So if you can write the forward logic, then they can compute the backward gradients, and using those backward gradients, back propagation, you can then train the whole network. So the chain rule and the back propagation all is taken care of by the framework itself. What you have to do is you have to know and understand the forward propagation and modify the forward propagation accordingly for your problem statement. For example, in one of the problems like many to many application of RNN, right? Like the one we saw here. In case of this many to many application, you will have to write a forward propagation appropriately, which takes in all these words sequentially and then is able to generate the result in a different language. But once you have written the forward propagation, the backward propagation can train this network appropriately. So let's take a look at how the forward propagation of RNN looks like. So don't worry about this equation. We will cover how this comes into being. Just notice that there are three weight matrices here, this one, and then these biases. So the RNN receives an input, and at any time this xt input, then it gives an output which is y here, which is ht at any point of time t. And in case of CNN, that is all you do. But in case of RNN, you have an input xt, you give the output yt, but there is also a feedback loop. Now let's look at how that feedback loop actually works. So here you can see that you get the input xt, you do something with it, and you give the output yt. And there's a feedback loop. Now let's look at how the feedback loop works. So we basically unroll the whole RNN throughout the time, and then we look at the forward propagation. So at time t equal to 1, it will basically take the input multiplied by weight matrix. Then it will generate the hidden representation. The H is for hidden representation at time equal to 1. And then again use another weight matrix to generate an output, another weight matrix to generate the next hidden state for H2 for time equal to 2. So basically you can see that the operation is such that the RNN uses three weight matrices, takes the input, generates an output, and also generates the hidden state for the next step at the next time step, right? And then again in that next time step, again the input comes, hidden state is used, output is generated, and a new hidden state is created. So this process goes on, and that's how the RNN forward propagation works. So you can see that overall the equation looks something like this. So this is the sigmoid function, and this is the nonlinearity that we use in case of RNNs, which takes in basically a weight matrix multiplication of previous time step hidden. For example, here this guy will be multiplied with a weight matrix, and then the input is also multiplied with the inputs weight matrix wx, and that is added and then passed to the sigmoid layer. So basically input multiplied with a weight matrix, previous hidden multiplied with a weight matrix, passed to a nonlinearity, and that giving the output, right? And this keeps happening continuously. So overall, if you unroll the RNN, this last time step will be something like a deep chain of these inputs and previous hidden states being multiplied together. All right. So let's kind of look at what is the parameter sharing in RNNs. So basically you can notice that there is three matrices, right? W, HY, WHH, and WXH. All these three matrices have specific roles. Now, are these different from these? Not really. All these weight matrices are same actually. They're all same. They're shared across time. Basically, the weight matrix remains the same, and each time step, the input is multiplied by the same weight matrix. Similarly, for the hidden also, it's the same, and even for the output also, it's the same. The weight matrices are all shared across the time, while the input keeps varying throughout the time steps. The hidden state also keeps varying. Now you want to calculate the loss function also for an RNN, and how can we do that? Like for example, in case of let's say something like this video networks, right? Wherein we had a video where one frame of video came in each step. For example, here you can say that x1 is one frame of video, x2 is one frame of video, and so on. Now each step of video is coming in, and within the video we have to do some annotation. So if we successfully did the annotation, then the loss here will be low, otherwise the loss will be high. So what we do is in each step there is some loss computed on each time step, and that will work for the video networks, right? Like in the second frame also we have some loss, in the third frame, and all the frames we have some loss based on whether we could recognize whether the object is present in the video and we correctly recognized it or not. We sum up all the losses, and basically that becomes the total loss of the RNN. So let's visualize the unrolling once again in a little bit. As you can see, this keeps repeating continuously over each time step, right? So the RNN itself remains the same, only the hidden state and the data changes. It keeps remaining the same, but the data and the hidden state changes and goes to the next step. Similarly, once again, another representation. The words are basically changing, the input words. The hidden state also changes, but the RNN remains same and is just reused at each time step, and the RNN is composed essentially of 3 weight matrices. Now, the way that this RNN's loss is calculated is also called as back propagation through time. So what we do is we forward through the entire sequence, and at the end of the sequence we compute the loss. That loss we discussed earlier, wherein it could be frame by frame loss, or it could also be that at the end of the sequence you will have just one loss coming from here in case of sentiment analysis, and then that loss is back propagated through each of these nodes. Basically the weights are shared, but back propagation will enable us to compute at each time point what was the contribution to the error, and then that will be used for upgrading the weights. So we will take a small example here, like for example, how do you predict the next word if or the next letter, for example here, next character in a word, and how can you do that? So for example, our training data will be this word hello, and we will do a one hot encoding basically to denote which letter is incoming, and these letters here this way will be represented as one hot encoded. Next, this one hot encoding. Now, the reason for one hot encoding is we cannot feed anything other than numbers to the neural network. It is essentially doing matrix multiplications, and as such, feeding letters is not possible. So we have one hot encoded them. Next, what we do is we will train the RNN to predict the next character. So it takes in this, it multiplies the first character with the weight xwx, which is the weight to be multiplied with the input. It produces a hidden state, and next with that hidden state it also produces an output by multiplying the hidden state with the hy why matrix, and that produces our output. The output is then decoded and we get the next character. Now this next character will be fed along with the hidden state into the network again, right? So this E is fed through here into the network along with the hidden state, which WHH takes care of, and the hidden state here multiplied by WHH comes here. Then that is used again in the same form as before, and that predicts the next letter. Something like this. And finally, the loss is basically whether I predicted each of these letters correctly, and that's the loss function here. So how do we basically test this? So for testing, what we do is we basically start with something like first letter, one letter, and then we try to get the next letter, right? So whatever the next letter is, we do a softmax or a just normalize it by doing a softmax normalization distribution, we get the next letter, and then we feed the next letter into the RNN again, along with the hidden state from here. So we keep doing that. We keep feeding the next letter that is generated in the previous time step continuously into the RNN, and that helps us generate the overall text. So one thing, this thing is basically called as autoregressive generation. So autoregressive basically means that you are taking the previous time step and generating the next, and you are taking the previous time step result and generating, using it as input to the next time step for generating again. All right, so RNNs suffer from something called as forgetfulness or long-term information problem. So what basically happens is, if you notice that the RNNs keep taking the input at each time step and adding it to their hidden step, hidden state, and every time step, what would happen is that the input which came pretty far back will keep getting smaller and smaller representation in the hidden state. So for example, what here, which is represented by the color black, becomes pretty small as you keep going ahead, right? And that is one of the problems wherein the RNN will completely forget what the sequence, the initial part was. Like here, there is a sentence, right? These movies were directed by very famous directors and a lot of money was spent over many years. As a result, they are very impressive. Now, what does this they refer to? They could refer to these movies, or they could refer to famous directors. Now, since we have a good long-term memory, so what we are able to determine is that they refers to these movies here. But an RNN may make the mistake that it refers to famous directors simply because it is forgetful and it forgets this older context. So we have some new kind of networks which are basically called as long short-term memory networks, and these networks enable us to make sure that the forgetfulness problem is minimized. So we basically change the major part of the network, which is the RNN, into a LSTM. LSTM network has basically 4 different gates. So basically, these 4 gates are enabling the network to kind of remember more. And it also has a memory cell wherein the information is stored. So the 4 gates of the network, there is an input gate which takes in the input, and its responsibility is to basically modify the input in a way to be used within the network. There is a forget gate which is responsible for determining what information to keep and what information to remove from the memory cell. There's an output gate which finally takes all these things and makes an output. And then there is the memory cell, which is basically storing the context from the past. Now, I want to get into something else, which is called as bidirectional RNNs or bidirectional LSTMs. So before we go into the bidirectionality, let me just elaborate a little bit on LSTM. So LSTM networks basically come with a lot more parameters than RNNs, and as such, while they are able to remember context long term, but they also are more expensive to train. And as such, if let's say the context that you care about is just a few time steps back, like let's say if your sentences are just 16 words or 32 words, then an RNN will be sufficient. While if you have really long sentences, like let's say 256 words or 512 words in a whole essay, then in that case RNNs will have forgetfulness problem, and it is better to use LSTMs. Now, another thing to note is that LSTMs, RNNs both are directly available in PyTorch, and you don't have to hard code these equations yourself, but rather the framework again helps you do it by default. So, okay, now let's get back to bidirectional RNNs. Now, what are these bidirectional RNNs? Bidirectional RNNs are basically based on the fact that not only the past is important for understanding, but also the future is important for understanding. So in that sense, what the bidirectional RNN does is that it does a forward pass in time, and then it reverses the sequence. Basically, it completely inverts the sequence, and then does a pass which is reversed in time, and then the forward and backward reverse directions together are summed up, and that gives the output. So this way what happens is that at any point in time you will not only look at the past, but you will also look at the future context and use that in your network. So where can this be useful basically, right? Like in case you are using a network which has to make predictions in the next time step, this is not going to be useful, right? Like if you are trying to predict the next one, this is not going to be useful. If you are trying to predict the something like rainfall, or something like whether tomorrow the sun will rise and shine, or whether it will be rain, if you are trying to predict weather patterns, anything like that which depends on predicting the future, this bidirectionality will not work. But if let's say that you have the whole sequence, like for example you have a IMDb movie review, or you have a uh, sentence, or you have a Amazon review, you have the full thing, and then you want to do sentiment prediction on top of it. In that case, a bidirectional RNN representation is going to be useful, because you have the full sequence. You are not trying to predict the next word or next something, but rather you are just doing something on the whole sequence. So in that case, bidirectional RNNs are very useful. They are more powerful than unidirectional RNNs, which only go through one direction. Think of it as being able to refer back to what you have read, rather than just relying on reading it one time. Like this refers to basically reading it one time and doing it, while if you are doing bidirectional, basically then you are kind of being able to refer it back. So now I use this word referring it back in a loose sense. It is not exactly equal to that, but it's kind of analogous to that. And there is something else which we will go into, which is very, very similar to being able to refer to the past directly, instead of taking a long tour to the past. So that thing is basically the word that we use for that is attention, and I will elaborate on why attention is needed in this example, wherein I'm basically doing machine translation. So machine translation models usually have two parts, a encoder and a decoder. And let's see how a machine translation model works. So encoder basically takes words one by one, as in here. It produces one hidden state. That hidden state is taken by the decoder, and then the decoder decodes the overall and produces a translation. Now notice how this encoder produced only one hidden state from here, right? Like if you see this again, the encoder, it takes in multiple words, and just like how an RNN would do, at the end of the RNN, it produces one hidden state. Now the problem with that one hidden state production is that will not that will suffer from the forgetfulness issue that RNNs have, right? Like there is only one hidden state here, and there are multiple words here. So that hidden state may not represent all the words equally. So because of that, what we use is something called as attention, and I'll show you what attention is basically doing. Yeah, let's look at how attention works. So attention also has a encoder decoder, two models that are doing this, but there's the difference here. All the hidden states are kept, and then they're used in the decoding stage. So let's do this again. So the encoder, even in the case of attention models, takes the words one by one, produces a hidden state for each of the word, but then all the hidden states for each word is kept, and they are used in the decoding state for producing the translation. So all the hidden states from each word is kept, and they are used in the decoding stage. That's the major difference between attention and between a normal machine translation using a encoder and decoder. So in attention, we kept the whole hidden state
of each word, and then we did something called as attending to each hidden state, and then that was able to produce the decoded output, which is a translation. Now this attending to the words, each word's vectors or each word's hidden state, can also be called as being able to refer back or being able to kind of look and refer back by turning over the pages behind, right? Like, so basically this enables the model to completely skip the forgetfulness issue, because it is able to refer back to anything, even the first word's hidden state is here. So this completely solves the forgetfulness issue, but attention also comes at higher computation cost. So what happens in attention is that you basically compute a attention matrix like this. Like when we were doing a decoding, what we used to do is that whenever one word will come, we will compute how much this word, this output word, is dependent on each of the input hidden states. Similarly, for example, here both am and a both are dependent on this word in the input, right? So this hidden state influences both these outputs. So while giving out these outputs, we compute at each stage how much this word will depend on the words that are in the input. So basically attention does nothing but compute a dependency matrix between the output and the input, and this dependency matrix is then used as a guidance while giving the output, and that makes sure that there is no forgetfulness, because all the whole of the input, like all the input words, are taken into account. Now that gets us into a simple question: can I do attention inside the encoder itself? Like we did attention between the encoder and the decoder, can I do attention inside the encoder itself? And yes, that is also possible. That is basically known as something called as self-attention. So in the self-attention scheme, what you do is that you run the RNN or whatever your model is on the input words. Then once you have run them on the input words, what you do is you do a self-attention layer, and the self-attention layer will update the input words themselves. For example, this word, it will be updated itself by taking into account what words it depends on, what words does it need to look at. So the self-attention block will update the hidden state of it and every other word in the overall sequence by basically looking at what it depends on and computing the self-attention matrix. Now the advantage of this is that you not only have attention between your encoder and decoder, but even within your encoder, between different layers of RNN, you can have this self-attention operator, making sure that there is no forgetfulness happening. You can also build pure self-attention based networks instead of RNNs, and those are called as transformers. So in that case, only self-attention blocks will be stacked on top of each other without any RNNs coming in between. So in this case, what happens is that self-attention does not have any information about what was the position of the word. Like RNN has information like what word came before and what word came next. Self-attention does not have any information on position. So what we do is we give it something called as position encoding, wherein we tell it that this word is at position number 1, this word is at position number 2, this word is at position number 3. So we just one hot encode the positions and we give it into the encoder itself. This is one of the caveats of self-attention, wherein it is not position aware. So without position encoding, self-attention will not work. It will basically treat all the words in a sentence as a bag of words rather than a sequence of words. Now, the next thing to look at is how do you use those words themselves, like both in case of self-attention and in case of RNNs, how do you use the words? Like if you remember the previous example where we used and generated a character level model. We were generating characters and we generated HELLO, hello. So in that case, what happened is that we were one hot encoding each of the letters, right? But in case of words, the number of words is very huge. Like there are maybe more than 5 lakh words, like 500,000 words and more even than that. So basically one hot encoding words will basically mean that the one hot encoded vector will be very large, right? There will be one in one place and then there will be like 500,000 zeros. So basically one hot encoding of words will not be very nice. So what we do is we encode the words themselves. We do a embedding of the word itself. And here what we do is we do a word level embedding. So each word will basically have one row in this big table. This big table will be 50,000 or more, like it will be basically the size of our vocabulary or the number of words that we are ready to use in our model. It will be that long, that many rows, and the embedding size, which is the number of columns in the table, will denote what size of hidden state or what number of embeddings do we want to use for each word. So for example, here one word will be represented by this many columns. This will have basically arbitrary numbers which will be trained during model, and they will begin to represent the word as the model is trained further and further. So this way, when a word comes in, for example, this word comes in, then we will just pick this particular first row. When this first word comes advark, then we will just pick up this first row as its representation, and that representation here will be fed. So the first row, if the word here was advark, then the first row would be this, and that will be the representation of the word that will be fed in. Small details about these BERT and BERT models. So when this number of columns is 768, then it's usually a small or a medium model. While if it is 1024 or 1280, this number of columns, then it's a large model, and 1600 basically means extra large models. All right. So again, just showing you the representation here, and the token embeddings here are taken in this way. Like here you can see that from the first row, the token embedding is taken, then the positional embedding is taken, they're added together, and then they're fed into the self-attention models. Now I want to discuss a little bit about a important concept. So this is basically how BERT was trained, right? Google has developed a model called as BERT, which is also used in their search engine, and many other places BERT is used for various NLP tasks. Now, why is BERT so successful? So one thing BERT does is that it uses something called as self-attention blocks instead of RNNs, and that enables it to skip the forgetfulness problem. But that is not the only reason for success of BERT. There is a secondary reason for success of BERT, which is that BERT trains without any labeled data. Basically, you can train BERT on just plain text corpora without any labels. How does it do that? So BERT basically takes the task of predicting masked words. So you will basically take a sentence, for example, let's stick to improvisation in this kit. So you take this sentence, and what you do is you mask one or two words from this sentence. So let's stick to improvisation in this kit. You will mask it and you will say, let's stick to mask in this kit. And now BERT model's responsibility is to predict what this mask was. What was the word which was basically hidden from it? It has to predict. Now, given that it is only predicting what word was hidden, so you can just feed it plain English sentences with word masking, and then you can use the loss function as whether it predicted the word mask properly or not, and then you can train BERT that way. So because of this plain English text from Wikipedia and general internet was used to train BERT, and BERT was very successful because it was trained on large data and without needing any human labeling effort. So how do we use BERT? Let's look into that. We use BERT in something called as transfer learning setup. So in transfer learning setup, what we do is we find a model which has been trained on large corpora, and we then apply it on our smaller data set to basically get a good performance. So for example, here we say that in transfer learning, we find a similar data set, train a model on it and test it and apply it on our use case. So we need to find a similar data set. In this case, what happens in NLP is that we consider most of the texts as a similar data set to other texts. So we start with a model which is trained on Wikipedia and Reddit and general internet Q&A data sets. We train a model on it, which is BERT, let's say. BERT is very frequently used. And then we test it and apply it in our case. Like, for example, in our case, we can apply BERT models to sentiment analysis. We can apply BERT models to also do translation like work. But those models are pre-trained. So we are basically transferring their learning that they got on some text corpora via their pre-training, which was basically predict the word that is hidden from you. And then we use that pre-training knowledge in our problem statement by fine-tuning the model on our problem. And we will see an example of this on code and how it is helpful. So here is some more information about transformers. These links will guide you into both the mathematical details. For example, this one gives all the mathematical details of transformers, and some of these other links have also good illustrations to guide you through how the mechanism works overall. All right. So I am not going to discuss this. The general trend that has been in the industry is that if you have huge amounts of data, large enough data, then sometimes architecture is no longer important, but rather the data and the data quality becomes more important. And even a simpler architecture can actually outperform very complex architectures. So data quality and data quantity are important things to look at when you are solving a machine learning problem. And in case you can get more data, in case you can get better quality data, always go for that before going for improved architecture or more computation. Always hunt for data before you hunt for architectures and for more computation power. All right, so what did we see today? RNNs, we use them for modeling all types of sequences, videos, audio, machine translation, everything, right? Now, vanilla RNNs are simple and effective for short-term sequences, somewhere between 32 to 64 words, vanilla RNN can do. But if you have 128 or 256 words, then vanilla RNN will forget some of the words. LSTMs use something called as forget gate and a memory cell together to make sure that they can actually remember long context. LSTMs basically have 4 total gates, and all those gates work together to do this. Then we had also seen bidirectional RNNs, wherein you don't just need to look at the past, you can also look at the future to make a prediction. Basically, when you're predicting something like sentiment, or when you're doing machine translation, it's okay to look at the future, right? Like if you're doing machine translation, then you can look at the future words in the non-translated version. Like if you're doing English to French, then you can look at the whole English sentence from the past and the future, and then make the translation rather than looking at just the past and making the translation. Then we looked at transformers and transfer learning. Transformers and transfer learning are the direction that machine learning is going these days in NLP basically, and in sequence modeling also a lot. So attention basically enables you to skip the problem of keeping memory and remembering, because it essentially keeps the hidden state of all the tokens. Since you keep the hidden state of all the tokens in attention, you don't have to worry about forgetting. and it's kind of like looking back and referring to something and then improving your idea about what the overall thing is. So attention basically refers back to each previous word and then improves the representations gradually. Then we looked at transfer learning with pre-trained models. Pre-trained models like BERT basically are already trained on huge amount of text corpora like Wikipedia, and we then transfer them to our own problems like small problems and sentiment analysis like problems, and they help us get a good performance. Next, we will look at a problem statement and see how we can solve it using transfer learning. As always, any questions you can ask in the Q&A after this session. All right, let's get into the lab session. So we will basically look at the recurrent neural network and compare it with transformers and how pre-training and transfer learning can help us. So we are going to work on this Jupyter notebook, and you can upload this notebook directly into Google Colab, or you can also use your own laptop or system. And if you have Jupyter installed, all the libraries needed are put here itself. And we are going to work on the GLUE dataset. Specifically, we are working on the Microsoft Research Paraphase Corpus dataset of GLUE, which is basically a dataset composed of sentence pairs, and it checks whether the sentence pairs are semantically equivalent. Basically, do they mean same or not? So before we get into it, I want to show some of the things here, important things. So one of the things is this device parameter. So if you have a GPU device, then this will automatically pick up the GPU device. Otherwise, it will pick up your CPU. So if you do it like this, then you can always just simply use this device parameter and your code will be portable between CPU and GPU. It's very good for testing on your laptop and then deploying to a GPU device or to or running it on a bigger cluster of GPUs. All right, so let's look at how the Microsoft Research Paraphase Corpus looks like. So you have this here, you just run this cell, just click on Shift Enter and it will run the cell. So Microsoft Research Paraphase Corpus MRPC is basically composed of 3600 train, 400 validation and 1725 test cases. Today we are going to work with train and validation. Since the test set requires us to submit to a leaderboard, we will leave that for later. So let's check how the classes are distributed. So this has only two classes. Either they don't match or they do match. So 0 or 1. So we see that the class plot here shows us that more examples are of the matching type. Let's look at one particular example here. So it says that these two sentences are similar, and you can say that these do look similar, right? So, and there will be some which are not similar. So let's check that. Yeah. See the difference here. See, there's a major difference here, which is the valuation difference, which basically makes the major difference. And here, this is also a difference. So because of this, these two sentences are not semantically equivalent and the label is 0. So let's see how it actually does the overall thing. How do we make the model? So you take a tokenizer first. These tokenizers basically separate into separate words. A whole sentence is tokenized into separate words. So for example, here this separates this first sentence into basically tokens. This G denotes a word inside a sentence, and sentences and the beginning of sentence is basically defined by words without this letter start. You can see it has separated all the words separately. After tokenization,
So tokenization is this part. You can also tokenize and then make a numeric representation of the token. So that is being done here. So you get for each word a number basically. We will use these numbers to feed into our model basically, because words cannot be fed directly. Then we have some helper functions. This is for weight initialization. And then we have our model definition. So this is one of the important parts. We define two types of model for testing here. One is the RNN model. This is the RNN model here. The RNN model is nothing but a bidirectional RNN, and we'll specify some hidden sides. And the nonlinearity used here is ReLU. And then we also have a pre-trained model. This is the Robota model, which is a transformer similar to BERT, and this is pre-trained on Wikipedia and other large-scale corpuses. All right. And then we do a forward pass in each step for training the model. So one of the specific things I want you to look at is this NN.module. You can subclass the NN.module thing and then make your model, and you will define a forward method in it. So that forward method basically takes care of how can one example be taken in with some labels and then loss be calculated. As you see at the end of the forward method, I return the loss and the predictions. All right, and you can also see that I am using this device parameter regularly, wherein I am pushing whatever inputs are coming into the device. Again, similarly, we have defined our evaluation function and our training function. The evaluation function basically checks for accuracy, and the training function is similar to before. And you can see that here in these steps, the training happens. In these few steps, the training happens. And one of the important points to note is that once we have defined the forward propagation, the backward propagation is taken care of by the framework itself. In fact, you can notice here that once I define the forward propagation in a particular way, the backward propagation gets taken care of by the framework itself. And then we train the framework. So we basically process the data set by concatenating both the sentences together. And then we feed the labels. So both the sentences concatenated together, separated by a separator, like here, this. The first sentence is here, and then the second sentence is here. They're separated by a separator. This /s is the separator, and then we feed that with the label to the network. So let's look at how the network behaves. So first I try a RNN. So I try a RNN with two layers, 128 sized hidden. So basically 128 perceptrons in the hidden layer, and a two-layered RNN. I try that. And you can notice that RNN, when trained for 20 epochs with a particular learning rate, I have hyperparameter tuned this learning rate. You can see that it starts with around 35% accuracy in the first epoch, like here, and then it goes up till like 68% here, and it remains, it kind of hovers around on 68%, right? You can see that the loss is still decreasing. So why don't we train it further? So I did that. We trained it for further, and you can see that here it remains at 68%, while the loss decreases. The loss is 0.674 here, and by the end of this stage, the loss is quite low. It is 0.64 instead of 672. So loss has decreased, but the accuracy did not increase. I decided to train it even further, and for 20 more epochs, and what I see is that the accuracy still remains the same. The loss also stagnates finally. So we are able to get somewhere around 68% accuracy using the RNN, which is not a pre-trained model. Now let's use a pre-trained model, a Robota pre-trained model, and see what we can get. So for this Robota pre-trained model, I will only train it for 5 epochs, and we will see the results. So here it starts with 68%. In fact, in the first epoch itself, it has hit the accuracy of the RNN. In the second epoch, it stays similar. In the third epoch, it's already 80%. And then it hovers around in that range, 78 to 80%. So you can see that it started here went down, hovered a little bit here, and then again further went down. It is very much possible that further training will reduce the loss further and give us more accuracy. But you can see that even without further training, with just 5 epochs compared to RNN's 80 epochs, it is able to reach 78% accuracy because it's a pre-trained model. The total training time on my hardware was 11 minutes for this model, and for RNNs combined, it will be, let me check and tell you. RNNs, it was around 10 minutes. So basically 11 minutes of pre-training here and 10 minutes, 11 minutes of training here, 10 minutes there in RNN, but this performs much better because it's pre-trained on a large text corpora. So that concludes our lab for RNN and also our overall session on RNN. Feel free to ask any questions you have about RNN, multi-layer perceptron or CNN in the Q&A session that will be coming next after a small break. And hope you had a great learning experience. Hope you were able to learn well and deeply about RNNs through this session. Thank you.